Okay, so can you please confirm that you can see the presentation?
I see it.
Knowledge can be revealed in different forms. According to Plato, there are 4 stages through which knowledge can be perceived. The most shallowest of them all is called eikasia, and it represents the knowledge that is perceived via images, shadows, or reflections. The second stage is represented by pistis, which represents belief, conviction, or faith. The third stage is represented by dianoia, which represents understanding. This is the field in which usually the natural sciences bring knowledge in this kind of level, of dianoic level. Next, the fourth one is called episteme, and it represents the true nature of things. Now, there is a subtle difference between dianoia and episteme, and the best way to emphasize that is to recall an example given by Werner Heisenberg when he described this kind of things. So consider a person that is very close to you, that all of a sudden he committed a crime that you are for sure that he could not commit it. So you first of all, you hear that news that he had committed the crime. Now that represents an eikasia type of knowledge. Then you have your conviction that he was not, you're pretty sure that he didn't commit it. So that's your belief with regards to that event. So that's represented by pistis. But then all of a sudden, you're presented all the evidences that actually he did it, and ultimately even he confesses that he did that certain crime. And that represents the knowledge called dianoia. Now, if you all of a sudden you have all these aspects regarding the event, and you all of a sudden understand that he had to commit that crime, that's the episteme type of knowledge. Now, Heisenberg further emphasizes that the role of modern science is to distinguish dianoia from episteme. Now, between these four types of knowledge, there are there's a fundamental difference. The first three of them are of sensible nature, meaning that they can grasp through sensorial senses, so like seeing, touching, and smelling, and so on. While the fourth one, the episteme, is of suprasensible nature, and it's grasped through thought, through the intellect. This PhD thesis starts with a discussion regarding this type of differences between sensible and suprasensible nature of things. It does so in the first chapter, and it continues in the second, where it actually provides parallels with the fundamentals of quantum mechanics. And furthermore, it makes a synthesis between those two things in a chapter called quasi-mechanics, which I coined it in terms of showing that part of knowledge that would show quantum mechanics in a different way, not in a mathematical way, but rather through a metaphysics values. So when I'm talking about metaphysics, I'm talking about not spooky stuff, but like something what Martin Heidegger had fundamented. The thesis proceeds afterwards with the elements of computational chemistry, where I show the tools of quantum chemistry that are usually employed in this kind of endeavors by chemists when they're trying to figure out some different aspects of chemical systems. Now, all this is not just a review of all these methods, but rather it's actually a personal understanding and a personal achievement in things that you would actually now understand how to use. So for instance, you can use the tools of quantum chemistry very easily by just pushing buttons, but it's a little more complicated if you go deeper down in the quantum mechanical aspects lying underneath those methods and try to somehow visualize them and to understand them. If you do that, you have access to more advantageous aspects later on. So for instance, yes?
You have to get out, it's not sharing the presentation properly.
Okay, so.
You just share your screen instead of the presentation. Start sharing. No, it doesn't work.
Not even now?
Nu mișcă între prezentare, nu ne rugăm pe microfon.
Nu, puteți dumneavoastră să vezi.
Dați și că arată și întrebați dacă văd că e în situație de prezentare.
Just a moment, we have a small technical difficulty. We will set it in a few moments.
Ok, reveniți la prezentare atunci. Întrebați dacă văd, schimbați
Yeah, so can you please confirm that you can see the slides, and if I change them, if you see that they are changed?
Trebuie să faci slideshow. Nu poți lăsa așa pe margine să fie alea mici. Trebuie să intri în slideshow, altfel stă blocat.
If I might add, in Teams there should be the options when you share the screen that you can select which screen you are sharing from. That might be the issue, but yeah.
So, slideshow must be installed. Not like this. The full PowerPoint presentation in slideshow.
Go to view and then you'll see slideshow.
The little cup icon must be active.
Okay.
That's okay.
Now it works.
So you can see the flipping of the slides as well?
Yes.
Yeah, it's okay.
Okay, so have you seen this part?
Yes.
No.
Yeah.
Yeah, okay, so then I'll continue. Okay, so anyway, I wanted to emphasize that actually here in this chapter 2 is not only just a review of method, but actually I also do some things on my own. Like for instance, in the case of the non-relativistic and relativistic methods, I actually figured it out how to make some calculations on your computer in order to find out how, actually not to find out, to grasp more and understand better, for instance, the relativistic effects that appear in heavy metals, so, such as gold. So anyway, and then the thesis continues with the first chapter regarding personal results published regarding cluster chemistry, and these are with regards to hydrogen-rich metalloboranes. Start with an introduction. We'll present the Wade-Mingus rules that govern these systems, and then we looked at systems with 5 vertices, 6 vertices, 7, 8, and then we concluded. Chapter 4 is dedicated to the active site of sulfate reductase, which comprises a cluster type of molecule inside it, and I will present it in more detail in this presentation. So it ends with things like this. So the first story is that of the metalloboranes. Borane chemistry is very peculiar because it has an interesting behavior when it comes to boron hydrides. That is, they do not behave the same as their carbohydrates when they clump together. Meaning, when you add carbons together, you usually get strains of molecules, or they become aromatic. They become planar molecules. Well, the boron chemistry, actually, boron hydrides employ three-dimensional structures in which also they develop three-dimensional aromaticity. Now there is a link in a relation called the Wade-Wingo's rules that govern the electronic structure of such a molecule in a configuration and its geometry. Meaning that, for instance, if a closed structure which has an electronics, well, basically, depending on how many electron counts you have for cluster binding, you will have different types of geometry developed. So for so-called closed structures, you will have 2n+2 electrons, n being the number of vertices that the geometry possesses. So when you add more electrons, the geometry starts to open and becomes nido and arachno, coming from the Latin clausa, nidus, meaning nest, and arachnion, from the Greek word of meaning spiderweb. Now these boranes also employ so-called isoclosed structures. I mean, they actually adopt a different kind of geometry, less spherical, so less symmetrical than the previous ones, and they have a different type of different electron count. And when you when you mix them with transitional metals, quite often you get this kind of oblato series in which the antipodal vertices come together and actually form intermolecular metal-metal bonds. Now we were interested in this hydrogen-rich metalloboranes, and in order to study them, we start from the borane, the simple borane pentaboride, 9-pentaboride, 9 meaning that it has 9 hydrogens, so 4 of them are extra hydrogens, and they bridge actually a boron-boron bond, and they form so-called free center 2 electron bonds. Now these were known, they were first synthesized in the beginning of the last century and at the first half of the last century, and they were used for rocket fuels. And when they were trying to synthesize this molecule, they also stumbled upon this other version of the pentaborane, which had 11 hydrogen atoms, and which further opened actually the molecule. Now we wanted to study those molecules which actually have metal vertices in some of these places. So we were interested in the second and third row transitional metal containing systems. So we started with initial structures in which we permuted basically the metals in each available position, and we computed their stability. So for each isomer, we computed the stability, and then we just predicted that this should be the structure of that certain molecule. So in the case of 5 vertices systems, the available geometries were the trigonal bipyramid, which is also shared by the carborane version of this molecule, the tetragonal pyramid, which is this one, employed by this pentaborane 9, and also this arachnion type, which has further electrons in it. But also, it also might happen that one of the edges of the tetrahedron of the trigonal bipyramid might break, and you would end up with a edge bridge tetrahedron. So I will show you now. We started with the palladium and platinum systems, and we computed all the isomers that we had in mind, and we find that the structure actually that was the ground state was actually similar to that of the 11, so the pentaborane 11, given here it's a simple geometry. Now the electron count is also similar, so it's similar in the pentaborane and in this metalloborane equivalent. So it's no surprise that actually they share the same geometry. So I will go just very fast on how this electron count goes. So I will just show for these systems. So if we consider the pentaborane, each BH vertex has on its, so boron has on its last shell 3 electrons. Hydrogen has 1. The entire compound of BH has then in total 4 electrons. 2 of them go to form the boron-hydrogen covalent bond, which leads to 2 extra electrons that can be donated for cluster bonding. So each BH group actually donates 2 electrons for the skeletal electron count. The bridging hydrogens have 1 electron, and they donate it to the cluster binding. So that will lead total to total electron count of 16. The same applies in here, and with the metal vertex it's a little complicated. It's a little more complicated story. You start from the group number of the metal. So how many? So for instance, for platinum and palladium, you have 10 electrons shared on the last on the valence shell. Out of these 10 electrons, 6 of them will be employed in non-bonding orbitals. So you can think about it, those orbitals which are, so if you think of metal vertex here, you have 2 orbitals, the d orbitals, 2 of them will be axial and 3 of them will be equatorial. So you can think about it, those equatorial orbitals are being populated and they're not gonna be employed in the cluster binding. They will just be of non-binding character. So, and then 1 electron will go to the single pentadienyl ligand and will make it anion, and it will also make it aromatic. So that's how we end up with a total electron count, which is equivalent to this pentaborane 11, and also shares the same geometry. Now, if we go to the earlier lefter to the more to the left in the periodic system, we see at rhodium and iridium, we have less amounts of electrons, 1 per vertex, and that leads to a total of 14 electrons, and will also lead to this geometry of tetragonal pyramid. And this was actually for this class of, for the family of 5 vertices, this was, the rhodium compound was actually known experimentally before we did the calculation. So when we ran the calculations and we found the ground state, we were very happy to see that actually is the same as the one that they were synthesized years before. So that also provided us confidence that our methodology works. So then we went further to the ruthenium and osmium. You get lesser amount of skeletal electrons, and the geometry of the adopted structure becomes now a trigonal bipyramid. And it becomes very interesting when it comes to the rhenium compounds, because rhenium should donate 0 electrons. So that would mean that initially they will have a lesser amount of electrons that any geometry that will be dictated by the Wade-Mingos rules, and would be quite odd. But what the rhenium is doing, it's forming a double bond. So like I was telling you, those oblato series that they became actually squashed, and it became squashed along the metal-metal axis, and they form extra bonds in that direction. So then you have so the double bond will contribute itself with 2 electrons here, and actually it will lead to a total skeletal electron of 12, which is similar to the one that we saw at the ruthenium, and will adopt the same geometry. Now, very close in this geometry, very close in energy, another isomer, so this was the 5th isomer related to the ranking of all the isomers of these rhenium structures, actually adopts a triple bond. So that means that it will get 4 electrons, 4 extra electrons donated to the cluster, and that will lead to a total of 14 skeletal electrons, and we will expect to adopt a tetragonal pyramid, and that's exactly what the molecule is doing here. So the bond indices that we computed for all this, but they are not shown on these slides, confirm that the bond orders of these interactions increase in rhenium and these isomers. So then we went even further to the left in the periodic system, and regards to molybdenum and tungsten, and we now encounter a triple bond in the molybdenum case, which leads to the same trigonal bipyramid electrons. Now there's an interesting thing with the tantalum. Tantalum actually here, the only way to rationalize it is that tantalum actually adopts a 16 electron configuration instead of 18 electron configuration like usually the transitional metal do. So it's not, I mean, it's quite often that early transitional metals adopt this kind of configuration. So for it, the electron count therefore leads to the same 12 electrons. Now we did the same with the 6 Vertex family, and we published them, and then we did it with the 7th Vertex family, and then with the 8th. Now, at the end of the day, we had 8 structures. So in all these papers, we had 8 known structures, 8 previously known structures that were synthesized before we did the calculations. So, each case we actually found the ground state of the family that we were investigating to be similar with that known from the crystal structures. So out of about 50, 60 predicted structures, there were 8 that were already known, so we were confident that actually the other ones will be right as well. And it turned out like 2 or 3 years afterwards, I wasn't expecting it, that actually some people from Chennai were working on some other type of metalloborines, and like a byproduct, they had this kind of metalloborines that we were interested in. So they basically synthesized what we were interested in. And they confirmed basically that the predicted structures by us were the same as the one that they found later on in their solutions, in the crystals. So now we continue with the second cluster story, which is with regards to the active site of sulfate reductase. Now, before starting that, I will just briefly show you to emphasize that actually the tackling of this problem was harder because now we didn't have closed structures. So everything was, we didn't have anything like radicals or unpaired electrons in the metalloborine systems, which is quite different from the ones from the cases where from the cases you encounter in the active sites of enzymes. Right? They usually like to employ high spin states, so they have a lot of unpaired electrons. Now the problem with DFT is that sometimes it works, some functional works very good for closed systems, but they will not work for open shell systems. This comes probably from a certain because of their parameterization. But the idea was that we tried all the functionals that we were expecting to behave good with these kind of systems, but before trying, we benchmarked them on some other active sites of different enzymes that employ in their ground state different spin states. So, for instance, this is the active site of cytochrome P450 and has a ground state of high spin. If a water molecule comes and binds to it, that becomes a low spin. Now in the hemoglobin, that process it's not the same. If you add water here, actually the system remains in a high spin state. So that's a tricky thing because you will need to find that DFT that will actually distinguish between these two. And then the most hard of all of them was the active site shown here, in which the ground state was actually an intermediate spin state. Okay, so then we took all the available functionals from TurboMol, so this is the software package, and we looked for hybrid functionals and double hybrid here, like in this case. Now the idea is that if you have hybrid functionals, mean that if besides DFT methodology, you also add Hartree-Fock inside. Hartree-Fock accounts very well for exchange interactions, but they do not account for correlation interactions. So correlation, we have two electrons. The one will move according to the position of the other. No? Hartree-Fock cannot actually describe that very well, but DFT can. But Hartree-Fock can describe very well is this type of exchange interactions, which most easily is explained is that those kind of things that give rise to the Pauli exclusion principle, so like Lund rule. That's not a magnetic reason why those electrons stay parallel. It's an exchange pure quantum mechanical cause there. So if you do DFT, you do not have this cause, but you can treat very well the electrons, how they move with respect to the other, so from a Coulombic point of view, but you do not have the pure quantum mechanical part. So if you just add Hartree-Fock inside it, you might end up with, well, if you're lucky, that it actually will describe your systems well. The pure functions, so if you do not add Hartree-Fock, those kind of functionals tend to overstabilize low spin states. Now, this is because that's the way they were built. They were built, they parameterized many times in terms of closed shell systems. Now, if you add Hartree-Fock, you will overstabilize high spin states. This is because somehow you're overcounting these interactions. So the question is how much Hartree-Fock should you add in order to that it will give you a reliable description of your system. So that's basically what we did here. So we did with half. So we chose functionals that have half Hartree-Fock 0, 2, and so on. And we also added dispersion corrections, but not for the Minnesota family because they already had it in their parameterization, and we used double and triple zeta bases. So basically, we just gave a score for each functional on each model that I've shown you previously, and it turned out that the best functionals to use for us was the B3LIP, M06L, and B97D. Now we excluded this one because we didn't have, the program couldn't do certain types of jobs that we needed actually to confirm that actually the structures are very good. So for instance, we didn't have gradients to do frequency calculations. And we had to choose between these two, and M06L, it's more parameterized. And for this reason, we just decided to go with the good old classic B3LIP. So, and we started looking at this again, now at the active site, shown here, of the sulfate reductase with emphasis on this cofactor, on the cyroheme. So sulfate reductase in general is an enzyme which reduces sulfite to sulfide, and in doing so, it consumes 6 electrons. So this is a very powerful, energetical process. You need 6 electrons to do that. So for this reason, in the active site, the enzyme employs this cofactor, a cubane, formed of 4 ions and 4 sulfur atoms, which acts actually as a molecular pump. What it does, it gathers, so for instance, this one here would be here in this crystal structure. Some other proteins will come and bind to this protein and will actually give electrons, and then the electrons will end up to this cluster, and this will send them very fast and very efficiently to the catalytic iron that would actually reduce the substrate and perform this reaction. Now, the tricky thing, that's one of the reasons why the DFT was very hard to do. The DFT methodology had to be reviewed very well before doing all this calculation, because this is a very complicated electronic structure. So in each iron, actually, in this cubane is in a high spin state. And now, I don't know if you can see very well, but in one face of this cubane, these 2 irons, they will form a ferromagnetic interaction. They are coupled through a ferromagnetic interaction. On the opposite side, they will have also the two irons will be with each other in a ferromagnetic interactions. But with respect to the faces of the cube, they actually are in anti-ferromagnetic interaction. So that leads overall of a diamagnetic state. So for instance, when people did EPR, this one was silent, but in Mossbauer spectroscopy, they actually could see that everything is in a high spin state. The other cofactor is the cyroheme, which is in the same family of tetrapyrroles as heme, the more often encountered cofactor in enzymes, and they are coupled via cysteine sulfur coming from a residue from the protein backbone. In nature, the sulfur reductase is encountered in different organisms, bacteria and plants in general, and bacteria usually they're called dissimilatory when they just want to get rid of the sulfide compound at the end. So basically, they are breathing. So instead of putting the last electrons of the breathing process on an oxygen as we do, they put it in a sulfide molecule. And also in other plants, usually they use it to incorporate in sulfur-containing amino acids. Now the main reason we were intrigued why does this enzyme actually is using cyroheme and not heme? Because everybody's using heme. You see heme everywhere, but you do not see cyroheme that often. And actually, the only place where you see cyroheme is in this enzyme and in the enzyme that synthesizes the cofactor. So clearly it had to do something specific to the role that the enzyme is doing. So we first looked at the structures of heme and cyroheme, and when you look just at the porphyrin ring, the difference between two is that the cyroheme is less conjugated. They have two double bonds that are present in the heme cofactor, becomes now saturated. So that leads to a decrease of conjugation in the porphyrin ring. Now, first did a simple calculation of this only the porphyrin without the iron inside it, and see how does that affect the charge distribution on the nitrogen atoms, so the equatorial ligands that will hold the iron together there in the cofactor. And we see that while in heme, the negative charge is evenly spread among the nitrogen atoms. When the breaking of the conjugation occurs here, the charges are no longer equivalently distributed among the nitrogen atoms. They become depleted here, and the charge becomes accumulated here. So now that certainly must have some effects on the way the enzyme works. So we first looked at the energetics of this kind of the active site. So we employed several models for the active site in order to understand better the effects that are appearing there. So we started for the simple model when you just have heme or cyroheme without any cluster binded to the axial position, and we calculated the energetics in low spin, intermediate spin, high spin, and so on. Then we looked at, so this goes for two redox states of the iron in here, so in ferrous and in ferric species. Then we looked at the intermediate between the simple model and the realistic model, which employed a zinc cluster here. So now the advantage of zinc ion, so it shares the same charge as the cubane cofactor, that is +2. So by doing this, first of all, the computational part would be much more easier. And then actually you can see how the things are going here if you have a metal center around, in the axial position. But what this model fails to account for is the magnetic interactions that appear between the two cofactors. So like I said, that in the cubane cofactor, you have ferromagnetic and magnetic interactions. They also appear between the two cofactors. So then we also had the more realistic model of the active site, in which we incorporated the iron sulfur cluster, and we did that for parallel alignment between the spin densities. So from this iron and in this side, they were parallel, and in this case, they were anti-parallel. And we looked at the energetics of those things. We also calculated afterwards the redox potentials of these systems, and then we also looked at the strength of the bond, of the interfactorial bonds. So you might have thought that, okay, the enzyme uses cyroheme instead of heme because maybe it's attaching better to the cubane. So we calculated that as well to see how well that attachment goes. And also computed Meyer bond order indices. So now this is very interesting. Usually when you talk about covalent bonds, you said that it is one electron upwards and one downwards. So that's an alpha electron and one beta electrons. So usually say that the covalent bond, you have one electron and one electron. Well, that's the case actually that happens only when you have closed systems. With closed shell systems, when you have open shell systems, the moment when you have a radical or something like an iron that adopts a higher multiplicity, this story is no longer valid. So if you, for instance, in the iron case, if you have an excess of alpha spin, those alpha spin orbitals, so the electrons placed in those alpha spin electrons, will actually, because of that same Pauli exclusion type of interaction that pure quantum mechanical cause, they will be stabilized when compared to their counterparts, which are in the beta, they are in the pointing downwards. Now, when the orbitals will become stabilized, they actually contract as well. So they become more focused on the atom, they're more concentrated to the atom. The other effect happens with the beta, which now they are the minority spin, and now they become delocalized, they have become more diffuse. So for this is the reason why in this bond, so this one here, you will have more beta than alpha. So it's not like you have half an electron, you have actually half and then a quarter of an electron, this beta and this alpha. So, well, anyway, we saw that the decrease of porphyrin conjugation, so that is encountered in the cyroheme model, leads to a decrease of the ligand field interactions, coupled with the which leads also to the asymmetric distribution of the charge among the nitrogen ligands. The distances also are increased, and all this leads to a stabilization of high spin states. Now, this is actually what the enzyme really wants. It really wants to have the iron in a high spin state. So that's an information that we got, and is very helpful to understand better the active site. The redox potential becomes more negative when you have cyroheme, and it actually doesn't play any role with regards to the bonding of the two cofactors. It's the same. It's when you have ferric systems, I think it goes up, and when you have ferrous, it goes down, or the other way around. So it doesn't really. The enzyme doesn't really care about the bond between the two cofactors. It does not try to stabilize it or to strengthen it. Now, by the time that we were doing these calculations, a paper appeared in Science in which they managed to make the heme iron sulfur cluster equivalent of the active site, so in a synthetic one, and they proved that actually it works the same as the one with cyroheme, which is encountered in the enzyme itself. So then further raised the question, why on earth this enzyme is using cyroheme if the mechanism will work as well with heme? So then we try to look at the other aspects of the of what cyroheme might influence in the active site. So this is basically, from single molecular electronics subfield that usually aromatic and anti-aromatic systems, they can transfer charge in different ways, and it's always dominated by the way this conjugation appear and disappear. So that gives us a first insight that we should actually look at the charge transfer mechanism within this system. So the first thing we did was to look at this enzyme as a donor-acceptor molecule. So when you do that, you consider first the cubane as the donor part. So these are all the electrons, spin orbitals, so alpha and beta. And in this purple color, they are the virtual orbitals, so they are not the occupied ones. So these are the HOMO orbitals, and these are the LUMO orbitals in the cubane cofactor. And then if you look at the heme, the energetics are much lower. Now, the way donor acceptor molecules work is that by having a donor fragment, the electrons will be, when they are placed on the HOMO orbitals, they are much higher than the HOMO of the acceptor part. And the other way around, the acceptor part will have the LUMO much lower than the than the donor's LUMO orbital. What that means is that if you put an orbital here and then you excite that molecule, it will be much more favorable to go here on the acceptor part and not on the donor part, because it's less energy demanding. So that's what we did. First we just looked at the orbitals of simple heme, cubane, and cyroheme without them being connected, and we already saw that if you compare heme with cyroheme, the barrier needed for the excitation to occur, it's higher in the cyroheme version. So then we did basically the calculations with the models themselves, and we find the same thing again, that the cyroheme containing systems actually require a higher amount of energy to perform that excitation. So what that means is that it's harder to transfer the electron from the cubane to the heme or to the cyroheme part. So that means that actually the role of cyroheme is to somehow inhibit this charge transfer process. So with regards to our triangle, that means we have reached this point. If this is a Bianoia type of knowledge, now we know the cyroheme inhibits the charge transfer within the active site of sulfide reductase. But if you remember, it needed 6 electrons. So it's kind of odd. Why would you inhibit if you really want those electrons very hard? So then what we did, we went further with some more advanced quantum chemical methods, and basically we did experimental theoretical chemistry. So we did experiments using theoretical chemistry. In this kind of experiments, when you use this formalism, you treat the entire active site as a molecular junction, which you sandwich it between 2 electrodes, nano gold electrodes, and then you compute how the electron current would flow through this molecular junction. And by doing so, you will get information about how the charge transfer goes inside this specific system. So we did that, and we see that in the first case, we just realized that something indeed it is happening. Like the higher the points here means that higher the transmission. So it's more favorable for the transition of for the transfer of the electrons to occur. So then there are some channels that become, when you change, so heme is blue, cyroheme is red. So when you change from heme to cyroheme, this channel becomes inhibited. This one as well, and this one actually becomes promoted, and this one as well. So we got a sense of what's happening, but still not deep enough. And then we went to a further formalism in which we call the implicit non-equilibrium Green's function formalism coupled with DFT, in which you imply that basically these nanorods are there. This is explicit because in the model that you are computing, you explicitly add those nanorods, nanoelectrodes there, and compute the transmission in terms of them. In the implicit version, everything is, all that nanorod is actually here in this equation, the Fermi energy of that electron. So what this formalism allows you to do is actually to look specifically at electron conductances between whatever atom you're interested in your system. So they proposed, this is just a little thing, they proposed, when they did it for the organic single molecular islands, they propose that it's enough to just take the HOMO and the LUMO orbital, because those processes, those transfer processes are dominated by those 2 orbitals. But if you do that with our systems, you basically cannot do anything because HOMO is located here and LUMO is located here, and you do not have any high amplitude on the bridging atom. So if you are interested in how those electrons go, so you need those. So what we did actually, we just took all the orbitals and computed the conductance in terms of that. So then we looked at the available routes between those two cofactors. So if you have an electron on the cubane, so we start with the synthetic version when we have a heme here. So I have this sulfur. The most neighboring atoms located here have certain, let's say here, transmissions, conductances. The values in the parentheses account for the transmissions further. So for instance, this 0.2 means that from D3 to this iron, the conductance was much smaller than from here to here. So we looked at this. So these are direct routes that go through vacuum. So directly from this cluster to the edges of the porphyrin. And there is another different type of route which goes through the bridging atom, and it's the bridged route, and it goes through this cysteine sulfur and arrives here at the sulfur. Now, when you change the heme with cyroheme, what happens is that all these routes that are going, the direct routes, are becoming inhibited, while these ones, it's actually a little bit, they become a little bit promoted. No? So that's a very interesting thing. So this is what actually cyroheme is doing. It's avoiding charge transfer via direct routes. Now, why would you do that? If you just imagine that this is a system which continuously pumps electrons. So if you pump it via this route to this carbon, let's say, and then to this iron, well, you would develop a transient radical character here, because statistically you always have an unpaired electron there. If you go through this bridge, through this route, you'll have that transient radical character developed here. Now the difference is that this one is protected; it's underneath the cyroheme, so that radical cannot interact with the substrate or with the solvent, which is not true for the case here. The substrate might easily go and bind to this atom, and also the solvent molecule might also bind there. So all the sudden we found this is the reason why sulfate radicalism employs it, because it avoids those routes which actually furthermore, they also imply routes, the second step of the routes, which are very slow. For all these numbers here are much lower than the other ones that, or their counterparts, that if you would go through this route. So that means that if you transfer the charge via this route, you will have actually the electrons stay on a more amount of time on the porphyrin ring and not to go to the catalytic iron. So you need those electrons to go there very fast. So that's why you avoid those leaking channels that would actually lead to an inefficient charge transfer. And furthermore, then, if you just close that leakage, the cyroheme itself is protected actually from undesired radical attack from these intermediates of the and solvent molecules, which didn't come by much. It was already known that actually porphyrin rings and so heme structures prefer to transfer the charge through routes. So if you look at, so in the porphyrin, just in the porphyrin, they will transfer the routes via route. They will transfer the electrons via routes that avoid the central iron. So this one has a very low transmission, 0 points, compared to this one, which is 0.97, goes all the way around. So that was already known by the time that we did the calculation. So it's further proof that yes, this is what's happening. If you put the electrons on the porphyrin, it will stay there, and if it stays there, it's not good for the enzyme. So that all of this, so that leads us to this conclusion. So you basically, well, not you, the enzyme basically inhibits the through vacuum routes and promotes the ones that go through from the through bridge, and for this reason that I already discussed. And that leads to an episteme type of knowledge with regards to the question why the sulfate reductase employ cyroheme. This is why. And then we'll just go very fast through this part. We were interested afterwards how the cluster itself affects the reaction mechanism of sulfate reductase. So besides pumping electrons, how does it affect the way the substrate change in its reaction? So we did that by employing all these 22 possible intermediates in the previous models that we also discussed earlier. And we looked again how the reaction would evolve if you have, well, no cluster, a zinc cluster, or a iron sulfur cluster, and see how things are working in that way. And we looked at, for instance, we started looking at linkage isomerism. I give here an example in the sulfate adduct, so where they actually start. So this is the way the substrate comes to the catalytic iron. Now in the crystal structure, it's very clear that it's binded via the sulfur atom. Now our calculations found that actually binding via the oxygen atom is much more favorable. Well, that doesn't mean that actually the structure is wrong or the calculations are wrong. That just means that actually the enzyme has to put some effort in order to stabilize the sulfur isomer, because you need to keep all the time the sulfur here, because you need it all the way for the reaction. The oxygen may come and go. As you see here, there are intermediates which, especially the ones at the end, that they don't have oxygen anymore. So, for instance, if you bind here via oxygen and suddenly cleave this bond and get rid of the sulfur, you don't really do the reaction properly. You do it properly when you end it here. So the enzyme has to tune the surroundings of the active site, so the residues of the protein backbones, in such a way that actually, so they do it with hydrogen bondings and things like that, and in order to stabilize the oxygen isomer. And we also saw that actually this effect is it's smaller when you have the cluster there. So the cluster actually kind of brings them to the same amount of stability, both isomers. Then probably it's easier to stabilize the other one. And we also looked at redox isomerism where it was the case. So this implies that, for instance, like a compound like this so this is the equivalent of compound 1, but it has sulfur, not oxygen here. Sulfur 2 minus. Redox isomerism means that you might have actually an iron 4 here and sulfur 1 minus, not 2 minus. So you have both of them, and we encountered both of them, and we looked at them. The interesting part was that actually, usually in these enzymes, you have so when you harbor a species like this, usually in the porphyrin you have a radical character, which is located on the porphyrin. Now, in the sulfate reductase case, this radical character is not located anymore on the porphyrin ring, but actually goes to the cubane. So that's something. And we also looked at the crossroads along the catalytic cycle. So, for instance, I'm just giving this example here. So, you say you start from the isomer number 1, and you want to arrive from intermediate number 1, and you want to arrive to intermediate number 4. There are two ways in which you can do that. So you can start with the proton addition, water elimination, and electron addition, or you can start with electron addition, proton addition, and then water elimination. So you can do the calculations and see which one is more favorable and what's happening. So, for instance, here we have this is the energy levels of the first intermediate in all these models, and relative to them are all the others. So you see that actually it's more stable to go here, but then actually you have more problems getting out of here because you need more energy to get from here to here than from here to here. So we looked at this kind of aspects. In general, what we see is that by having the iron sulfur cluster present there, you actually stabilize the intermediate, so the process goes faster. than if you would not have it. So let's say you would just pump the electrons like you usually do in other redox enzymes, that they are not using things like this. They will go slower, let's say. So in the conclusion, we saw that the oxygen binding is it's more preferred, but also the cluster, the iron sulfur cluster, plays a major role in the reaction mechanism besides just providing the electrons. Okay, and with that, we'll present, this is the list of conferences which I attended during the Ph.D. program. Most of them were with oral presentations, some of them were also awarded. And we ended with, finally we ended with 9 publications. 7 of them are directly related to the present PhD thesis, while these 2 are unrelated with it. And with that, I would like to thank you for your attention.
Thank you very much for your nice presentation. And now I will invite Professor Radu Silaghi-Dumitrescu to present his report concerning the activity and the PhD thesis of the candidate. Please.
Okay, thank you very much, Professor Polish. I would like to confirm now my report, the written report, which is already on file with our doctoral school. I should start by saying that for me it's been a real privilege to work with Adrian. It's been very interesting, and I think we've learned together a few things, and we've learned from each other a few things about how to do research in computational chemistry and more than that. So of the approximately 230 pages of the thesis, excluding the contents, references and appendices, 9 represent a general introduction, 86 provide an original attempt towards fundamental problems of computational quantum theoretical chemistry, and that includes some personal contributions of the author, and the rest show the personal results as published or prepared for publication, manuscripts by the doctoral students. And there are also 200 pages of supplementary information, which include numerical data supporting the main text and the references therein. And then there are the bibliographic references, about 13 pages of those. And the general aim of the thesis, as you've seen, is to apply a set of computational or theoretical methods on practical problems in inorganic cluster chemistry. You've seen chapter 1 mentioned briefly here. It gives an overview of the thesis structure, of the objectives, and of the motivation of the thesis. Includes references to a set of basic philosophical notions that are then alluded to or referenced to throughout the thesis, highlighting the emphasis put on the students' attempt to generate useful data aimed at advancing knowledge with clear and practically relevant conclusions, as opposed to merely performing routine experiments with the purpose of mastering a set of scientific techniques. And then chapter 2 provides an original presentation of some fundamental issues in theoretical computational chemistry with extended original contributions from the student in terms of derivations or some phenomenological connections between them, or extending simply some interpretations. The considerations laid out in this chapter have formed the basis of the student's original contribution as co-author in the journal PCCP, which is shown on the screen actually. And then chapter 3, as you've seen, provides the student's original contributions in metalloborane chemistry, Over the course of about 60 pages, data from 4 publications are presented. The publications as listed on the screen again, where the student was the first author. These publications were the result of a collaboration with Professor Robert Bruce King of the University of Georgia in Athens, Georgia, United States, and Professor Alexandru Lupan at our Babeș-Bolyai University. Each paper is presented in a separate subchapter grouped under a title reminding the number of vertices of the respective hydrogen-rich metalloboranes. And you've seen it, 5, 6, 7, or 8. Density functional theory methods are applied throughout the chapter in exploring structural and electronic variability or plasticity in these sets of clusters, with clear accounts of, first of all, the degree to which these computational predictions have agreed with prior experimental data, and second of all, the degree to which they have provided novel or predictive contributions or new interpretations, and most importantly, the degree to which subsequent experimental work has since confirmed the students' computational predictions. Chapter 4 gives the students' original contributions in bioinorganic centers, clusters, mostly on the cyroheme iron sulfur active site of the enzyme sulfite reductase. As you've seen here, a considerably more versatile computational toolkit is employed, partly as a result again of the explorations set forth in Chapter 2. Though DFT methods remain at the center. The students' contributions in these areas have been mostly reported in publications, though some still are in the form of a manuscript. And we've seen the effort put into methodology, and I won't go over that again. There is a Chapter 5 which summarizes very briefly the conclusions of the thesis, as well as the directions where the research can or has already began to be going, including publications and manuscripts already in work. And in conclusion, I would say that the doctoral students project, Adrian's project, involves studies of potential practical interest related to the application of computational and theoretical methods in chemistry and biochemistry. The topic approached is technically challenging, and the student has in fact contributed personally to these complications by adding distinct personal methodological contributions. The results are clearly presented both on a technical level and on a more general level regarding their general relevance. It can be appreciated that the experience gained by the student in these investigations already far exceeds the one required by a certified specialist with a doctorate in the field to today's standards. The results of the doctoral students' research were presented in peer-reviewed publications with a high sum of impact factors, as well as at several international conferences, and the unpublished results are already promising. And then, considering the activity of the doctoral student during the elaboration of the thesis and the quality of the results described in the thesis, I did express my agreement that the thesis be publicly defended, and my agreement that the title of scientific doctor in chemistry be awarded to the doctoral student Adrian Brânzanic. And I certainly congratulate him for the hard work. That's about it.
Thank you very much for your nice words, my 2 words. And now we'll start the second part of the defense. Now will be the second harder part of the defense. I will ask reviewers to present their assessment and also to present their questions to the candidate. First, I will ask Professor Ulf Ryde from Lund, University of Lund from Sweden, and please, it's your turn now.
Thank you very much. Do you hear me? Okay. So I suppose that I read my conclusions. So I have a report and the report contains the summary of the thesis that Professor Silaghi already have read, so I will not repeat that. So I will read my conclusions first. So I have written that in conclusion, the thesis is clearly impressive. It's one of the most extensive theses I have ever read, especially in the terms of number of pages, but it's also one of the most philosophical theses I have seen in chemistry. However, the amount of computation performed is also very large, and the scientific content is of very high quality and very interesting. The student has tried many different methods and calculated many useful properties. He has done this independently, finding new methods, trying new methods, and applying them to his systems completely independently. The presentation in the thesis is very good, and there are very few errors, and it's very easy to follow the lines of thought. Of course, with so many calculations, there are small errors here and there, and sometimes it can be a little bit hard to find the significant conclusions and all the results. But in total, it is, as I said, a completely impressive thesis, and therefore I recommend the defendants of the thesis, and also that the student should reward the scientific title of Doctor in Chemistry. And I must also say that it has been a pleasure to work with Adrian. He has been a guest in my laboratory twice at least. I also met him at some conferences, and my impression is that he works very independently, especially finding new methods, solving new problems, testing them on your own systems. It has more been the role of stopping you to do calculations rather than to suggesting what to do with your systems. So that's my conclusions. Should I also ask questions now, or what is?
Yes, please, you are invited to do that.
Okay, so then I have a few questions about the thesis. Since I have been mostly involved in the cyroheme, the sulfite reductase systems, I will concentrate on that. But I want to have a few questions also about the metalloboranes. So, Adrian, could you shortly motivate the choice of DFT functionals and basis set for these systems?
Well, shortly, because they work. That would be the short answer.
Okay.
You don't really get. I mean, B3LIP works very well with metalloboranes, and we also did all of the time we did the parallel with the Minnesota functionals to see if they, well, somehow to refine if in one. Well, where it was the case actually, but not all the time. But with those kind of systems, basically, DFT it's enough. You don't really need, higher. Not even the functionals. You don't really need a more, let's say, modern, more parameterized functionals.
Yeah. So, but why did you use a non-hybrid functional with the big basis set and hybrid with the small basis set? We normally do the opposite.
Yes, that's your point. But well, that was basically that was at the beginning of my PhD thesis. So that was already the methodology. So that's how things were done.
Yeah. Okay. You did.
I mean, at that point, I didn't play any large part in the technical part because I didn't quite understood them. So the metalloboranes can be regarded as a part where actually I prove that I'm a good technician, and the other part with sulfate reductase proves that yeah, I'm a scientist as well because I can understand those methods better.
Oh, that's wonderful. You did very many calculations here. For example, for the largest system, you did 187 isomers. How did you simply set up all these calculations?
Well, very hard because we did it first manually. So
you really did it manually. Wow.
So that's how you become a good technician.
Yes, that's impressive. In the thesis, you often say that the state is fluxional. What do you mean by that?
Well, basically so for instance, when you have fluxionality means that you have two isomers or two conformations which are very close in energy. So like in 5 kilocalories per mole or something like that. So basically you find them as different states in your computations, but in reality, the system will actually flip from one state, from one conformation to the other very fast. So for instance, there were cases, I think, where there were iridium atoms, and it was a bridged hydrogen, which was sometimes bridged, sometimes just terminal hydrogen. So that's a fluxional state because the energetics of them are not really, I mean, quantitatively, they're not very different. They're very close. So in reality, the system probably certainly goes very fast from one conformation to the other.
So you really see that in experiments that you have two different structures?
I think in experiment it was seen as well, no, yes, it was. In that case, I remember there were two isomers, yes.
Okay.
So we found those.
And then you never discussed the oxidation or spin states of the metals. What are the oxidation states and the spin states of all your metals?
Still talking about the metalloboranes?
Yes.
Yeah, well,
is it neutral? So
yes, you count them as neutral, basically, but it's a different way of thinking about them.
But I guess they are always low spin, so they are either singlets or doublets, or
yes, they are always singlets. That's the reason why we studied second row and third row, because singlets are more stabilized, and usually in experiments you find them as closed shells. But in the first row of transitional metals, you might also find this spin degeneracy as well. So you might actually look at more isomers and spin isomers. So that's the reason why we neglected the first row of transition metals to avoid that, because it would have been just too much. And bear in mind that at that point we were working on a very small cluster that we had it here in our faculty. Later on we had one at the university, but at that point we were very limited on the computational point.
But half of them must have one unpaired electron at least. Half of them are even spin, but the other half are uneven spin. So they must be doublets also, even if they are low spin.
Yeah, well, perhaps, but it's quite different because you formally treated it like that, but then when you put it in that cluster with borons and things like that, it changed. They're more. I mean, formally you would see it like a singlet or doublet in the ground state, but those electrons goes to the cluster binding, so they will not be actually present there formally in the metal vertices.
And since you have two metals, it will always be a singlet.
Yes, because basically that's the thing when you have those six electrons that are non-binding interaction, because they are not interacting neither with the ligand, neither to the cluster. So those are free orbitals which are filled. So then, yes, it's a singlet. It's a closed shell.
Okay. Let's jump then to the sulfite reductase. And since I have not been involved in the last paper, let's discuss that primarily. So Could you perhaps put up the suggested reaction mechanism? You had it on your presentation. It will make it easier to discuss.
Is it seen now? Can you see it?
No.
Oh, no, actually we don't see anything from half an hour.
No, we only see end of slideshow. Try to, yeah, exactly, and then share again.
Oh, wonderful. That's better now.
Okay, is it okay now?
No.
Okay, so now?
Yeah, perfect. So what oxidation states of sulfur do you see in this scheme?
Of sulfur.
Yeah.
Sorry, I didn't understand your question.
Which oxidation state do you see in the different states for the sulfur?
Yeah, well, you go from +4 to -2.
Yeah, exactly. And do you have all of them? I guess you have.
Formally, I believe so, but if you look at the molecular population analysis, yes, I should look there to actually answer you correct for sure. But yeah, formally, you have all these oxidation states, because basically you have, so you start with a species which sulfur is in a +4 oxidation state, and you add 6 electrons all the way when it comes here. So
yeah, but sometimes the electrons go to iron.
yes.
At least
Yes.
in this figure, I suppose that the formal oxidation state is first 4, and then it goes down to 2. I don't know if you had 3 anywhere. Yes, you have a few with 3, but then it jumps suddenly down to -2. You have 1 with oxidation state of 1, +1, but then you jump over 3 oxidation states, going from 11 to 12, and then you are down to -2 for the rest. What about experimentally? How many oxidation states do you observe if you also say that you don't allow disulfur compounds?
Well, I really don't know. I know that experimentally there were seen 4 intermediates or something like that, and then. Sorry?
For the enzyme, you mean?
Yes, so the intermediate.
Okay. Do you know which 4 they have seen experimentally?
No, but I know the paper where I can look for them. It's basically the paper which Professor Radu Silaghi has, well, initially has proposed this reaction mechanism. So it starts from, well, just a few intermediates. So they're not 22, they are like 4 or 5, which were known experimentally. And he basically looked at the unknown intermediates between the known intermediates. Okay. That was all the point of calculating all this mechanism, to know how they are connected, actually.
Mm. So from a first, if I look at it from a first view, it looks a bit strange, because when I do studies like this, I normally assume that the electrons and protons come at the same time. And for example, if you look at the second row, you see that there are 3 protons coming without any electron, and that, to me, that looks strange. I always expect that first that protons and electrons come at the same step, essentially. It's normally very hard to say which one comes first.
Yes, well, actually, this is the initial reaction mechanism. At the end of the chapter, we had the other one, but actually we see that indeed it doesn't really make any sense. None of these routes are favored. Basically, it's the same thing if going with the electron or with the hydrogen, starting with the one or with the other. So that translated means basically what you said, that this is the reaction at that point, at least, it's concertated with electron and proton addition. But so if you just look at the energetics, you see that they're very favorable. So you expect that in reality to go very fast then, indeed.
So let's go then to the energetics. You had a figure where you had these first 4 states, this one exactly. Mm-hmm. How did you get these energies? How do you get comparable energies when you have a different number of electrons and protons?
Well, first of all, you start from the first intermediates, and then you assign that as the 0 of your map. So you just put 0 here, and that everything else, all the intermediates afterwards, are calculated relative to that intermediate. So afterwards, so for instance, when going from from the intermediate 1 to intermediate 2, well, you have the energetics of the intermediate 2 because we computed that.
Yeah.
But now, so this is a reaction when you add a proton. So first of all, what you say is that this plus this should go here.
Yeah.
And then and I'm assuming you were aiming at this problem because how you compute the proton.
Exactly.
So that's it's a constant. It's a value that we just always in the calculations like this we add it. So that's the solvation free energy of a proton in water.
Okay. So
it's easier when you have the water molecule because you just compute the energetics of the water molecule. So when you have this dissociation.
Yeah. So what do you do with the water? Is the water in vacuum or in a continuum solvent, and if so, in what continuum solvent?
Well, everything is in continuum solvent. We optimized the structure in a vacuum, and then we performed the higher accuracy method. So when we did the bit-free LIP, so we use TPSS because it goes very fast. It's a pure functional and it goes very fast and it gives good geometries. Yeah. But bit-free LIP we saw from the benchmark that actually gives better description of this system, so it's more reliable. So then when we did let's say the bit-free LIP correction, we also included the continuum solvent. So it's like yeah.
But it's epsilon 4 continuum solvent and not a water solvent. Yeah. Okay.
Yes, but the water dissociates in the environment of the protein, not in a. So yes, we use the protein environment constant 4.
And the electrons you do the same thing. You add a constant.
Well, no, you don't do that because you just when you add the electron, you already have it in the next system. So it's just the difference between the intermediates.
Yeah, but you have two different systems with a different number of electrons.
Yes, so this is like computing the electron affinity. So going from here to here.
So you're not adding any constant there?
No.
Okay.
You just make the difference, and that accounts for the electron affinity. Or if you go the other way around, it's electron ionization potential.
Yeah, okay. Well, then I know how you calculate it. And you don't add, these energies are enthalpies essentially, or rather pure energies, not free energies. So you don't have any.
Yes, there's no free energy here.
You don't, because every time you dissociate something, you gain some 60 kilojoules or 15 kilocalories from translational entropy.
Yeah, well, the information is there because we did the frequency calculations as well, but those are done, so that's at the TPSS level. So yes.
But they are not added to the energies you present here.
No, I mean they are there in the calculations, in the output, not in the results.
Oh, okay.
It just complicates everything because we have the geometries at the TPSS level, and then you calculate the entropy contribution at the TPSS, but then everything else you had at the B3LIP, and you normally should do the frequency calculations at the B3LIP again, which just takes a lot of time as well. So that's the reason that I didn't thought of doing them, or not yet, at least.
No, I just wanted to know exactly what you have done. Because I suppose that once you add protons and add electrons, that you're missing the source of the proton and electrons. So you're missing the effect of pQA and missing the effect of the reduction potential of the donor of the electrons. And that would change your curves quite significantly if you add them.
Yes, well, I assume that it's better. You could actually correct that if you do QMMM calculations.
Yeah, it's very hard.
Yeah.
It's extremely hard to do calculations by this, but in principle, you could do that. Yes. Now let's see. And the cubane, when you included that, you used which state of the cubane? You used the oxidized state, as far as I remember.
Yes.
But which broken symmetry state did you use?
Okay, so just let me find the. Yeah, okay, so broken symmetry implies that, well, first of all, you start with a normal DFT calculation in which you basically assign the highest spin state possible to the system. So for this enzyme, it would imply that all the ions are in high spin state. So you do that calculation, you converge that, and then afterwards you do the broken symmetry, which means that actually, so if this ion was initial also an alpha spin majority, you flip it and you have it now as a beta. Now there are several, yes, I know where you're going with this. There are several states of spin states that are asserted here, but then that's the crude approximation that we did, that we are treating that all of those are basically somehow equivalent, and we are more interested in how the overall, in the vicinity of the heme, so the overall, not the overall, the local spin density, which is in the vicinity of the cyroheme, is oriented with regards to the spin density on the iron. Now, I know we did that, and what we actually did was always try to, not tried, actually that's what we did. We always kept the same spin state in the cubane. So it was something like that. In this parallel alignment, this iron was parallel to this iron. So then the one next to it was also parallel to them. So then you would have so-called super exchange interactions mediated by this sulfur atom between parallel iron atoms. So if these two are then parallel, this two has to be antiparallel. So that's the state that we always looked, and that's the thing that we called parallel alignment. And then we also did the antiparallel alignment. And Yes, I assume you are now referring to the substrate with the reaction mechanism cluster. What?
No, I only wanted to know which of the 6 possible broken symmetry states you used in the calculations, because you don't specify it.
Yes.
Further projects.
Yeah, I think
for the first 2 projects, but not for the third one.
Yes, I think it's the parallel one. I always use the parallel one.
Okay, fine. Why didn't you try to use also the reduced state of the cluster? Because to me, the important of the enzyme is that you can do 2 electron transfers with the cluster. And that possibility you turn off by not studying both states.
Well, yes, but that will just double the amount of work that you have to do, first of all.
That's true.
And now let me just get this straight, because the idea is that the enzymes that are using solely the clusters work different than the ones that, different from the one from the sulfate reductase. So if I remember correctly, sulfate reductase goes from the oxidized reduced, so from +2 to +1, and those high PEEP, the high potential iron sulfur proteins, I think they go the other one. But anyway, there are two redox states coupled, so that you can do with the cubane cluster, and that's why actually it's quite good, because basically it doesn't really change geometry like the metalloborane do, for instance. When you just change the electron state, you change the geometry. The cubanes always basically stay in the same configuration, and this is mainly because those HOMO and LUMOs of the cubane in the oxidate, I know for certain in the oxidate state that they are of non-binding character with regards to the bonds inside it. So we did that as well when we did the calculations for the donor acceptor treatment. Because at that point there were some tricks that it could have been an entire presentation only about the tricks employed in order to do those broken symmetry calculations there. But the trick there was that at one we were interested in doing to model when this guy is reduced and this one is oxidized. Because at the beginning I did it all the way around, and I didn't understood why nothing made sense until 2 years ago you pointed that out, that yes, actually when you want to model that, you should treat this as in the reduced state. So at that point we did that, and then we flipped. Actually I assign the charge state on this iron, and then I just flip those irons in the input file so that I could model this one as a reduced. So for instance, if this was initially ferric, so in the oxidized state we just put it as reduced, and then in the input we just flip the coordinates. So then this guy is here and this one is here. So then this thing becomes in its oxidized state, and this becomes in its reduced state. So because that's what's happening. If you start with oxidized, from somewhere you get the electron, it becomes reduced, and then the LUMO associated with this state will be here. So that's. But probably so it's one thing when you calculate how the virtual orbital would look, and it's a different thing when you actually put the electron there. So, but it gives, nevertheless, it just gives you an idea of how, and that's basically the entire the donor acceptor treatment.
Yeah. Okay, a last question. You say that your calculations prefer that say sulfite binds by the oxygen, but that the protein prefers sulfite binding by the sulfur. And you say that this can be changed by hydrogen bonds. Do you know what hydrogen bonds are available in the active site?
Well, not really. I mean, Well, let me tell you how I would remember what kind of residues are here. In the moment when we actually had a chemical communication paper, at one point I had to better specify why. I mean, some arguments had to be done more properly. So at that point, I had to read more about self-hymns and how self-hymns are generated. And I remember that in self-hymns, so I mean not in self-hymns, like in proteins, that hemoglobin and myoglobin, at one point they also form self-hymns. So that's should be a heme here, so somewhere. So that's self-heme is something when you actually put a sulfur here and binds like that to the heme, to the proximity of the porphyrin. And I remember that, well, that has not, the proteins and the organisms are not doing that because they want to change the protein, but they're using the sulfur there just for signaling purposes. And I remember that at that point, at one point they said, I think they were lysine residues that they said that actually favor the formation of self-hemes around here. And when I looked at the cyroheme, I can't remember if I saw the lysines or something similar to them. And I argued that probably because of that residue environment, it will actually facilitate the formation of self-hemes. So that's in the problem. And why would you avoid the charge transfers via the porphyrin ring? So I'm not really sure which are but there's something like that. Those are the residues, something like that. But I don't remember them clearly. I mean, I never knew them, basically.
No, but in the active site, you are absolutely right. I think there are 3 arginines and 2 lysines around the active site. So there are plenty of hydrogen bonds, mainly because there are so many carboxylate groups on cyroheme. That's another difference we haven't discussed, but there are actually 8 carboxylate groups around the cyroheme, but only 2. So
yes.
Plenty of positively charged residues around the active site.
So it's actually very interesting because cyroheme is a precursor in the biosynthesis of heme. And it doesn't, I mean, when you think about it from evolutionary, from just what we've discussed so far, it looks kind of weird. Why would this guy be, well, an intermediate in the biosynthesis of this guy? Well, it makes sense, probably like hundreds of millions of years ago, they were just using cyroheme and these kind of compounds, all the organisms everywhere. But if you read, I mean, if you look at how all these porphyrin rings are related, it makes sense actually, because all of them, so including the one from the chlorophyll and in the chorines in the cobalamines. So the cobalamine has basically a cobalt here, and this is just a simple bond. I mean, here in terms of this porphyrin ring, it's something like that. And in the chlorophyll, you have magnesium here, and you have different types of things around here, and a long antenna around there. But they all start from uroporphyrinogen 3, which is the precursor of everybody. And it looks something like this without the iron. And actually everywhere it has this carboxylic acids residues everywhere. So then it makes sense that this one is this one is a precursor of this one, because this one has less of them, meaning that, yeah, they were just cut off during the biosynthesis. So if you look at it from this point of view, it makes sense that, yeah, this is older than this one. Because this resembles more the original porphyrin.
Okay, thank you very much. It has been a pleasure to work with you, and it has been a pleasure to read your thesis. Thank you.
Okay, thank you.
Thank you very much. Now it's Professor Mihai Putz's turn. Are you there?
Yes, thank you very much.
So, please.
So, dear guests, dear colleagues and friends, it's my honor to be part of this commission. As always, I used to say, Babeș-Bolyai University, it's part of my curriculum since I done my habilitation there. So I have many friends in physics, in chemistry. So I salute all the members of commission, all the guests. I start with complimenting Adrian, and also complimenting for the discussion he had before, covering so many aspects of science which are in his thesis. I also read with very nice, with very much pleasure, all the argumentation in this, with all the still chemical things, all the computational things, quantum things, and I feel that I also appreciate that the candidate, feel the need after making so many computations, so many results, he find himself maybe in such a Socratean state. So he concluded that after all these complicated things, in the same things done in various formats, quantum mechanically, quantum chemically, he arrived to a conclusion that we know almost nothing about chemical bond. So, well, and that was very tricky and stimulating for me. And I thank again Radu inviting me. And well, at the end of the thesis, reading the epilogue was the starting point, making my report. So, because Adrian said there very drastic conclusion after such a big thesis, he wrote that. And I quote now, the driving force behind this thesis start was the understanding of the chemical bond. We have come to understand that the chemical bond belongs to the class of things that are not. Consequently, all other unicorns deriving from it, such as resonance, conjugation, hyperconjugation, covalent bonding, Doro, acceptor bond, agostic interaction, p-bonding, etc., share the same non-existence. From the quantum mechanic point of view, chemical bond simply does not exist, as no operator is associated with this quantity, and therefore no observable quantity either. At best, chemical bond information is chopped out of the wave function. So, and that stimulates my report because, well, I'm a physicist on the basis, and okay, made a passion for quantum chemistry after understanding deep quantum physics. So I stated also in my report, and I appreciate very much the propension of Adrian of embracing everything in philosophical meaning. And I appreciate also Socratean state he arrived at the end. But it's also the philosophy was not stopped to Socrates. Came after he came Plato, but he used Plato also. And then Aristotle, who is more pragmatic, and maybe he will like to accept and to continue, if you want to continue with this metaphysical quantum chemistry, also this side of the things, which I will next expose, and in which I was involved too. So I feel this miss in quantum chemistry some 10 years ago, because according with the quantum simple mechanics, the duality of particle and wave ask that each way of existence, either wave, either particle, ask for the complementary one. And this is true also in quantum chemical fields, in operator and whatever. So it seems that quantum chemistry stopped at the level of wave functions. So starting for wave function of electrons or atoms in molecules or whatever, it comes with interferential analysis. So the component original wave function combined, okay, goes to interferential and non-interferential, so gives to the occupied and non-occupied, and so gives all these mechanisms. But nevertheless, they stop to wave function and does not look, and in my opinion, was hardly not look to the correspondent quantum particle corresponding to this bonding wave function. You see, if you take two electrons in a free state, they interact, they are fermions, yeah? They interact, either are in attraction or in repelling by the boson called photon, okay? So the photons are the bosons intermediating the fermionic electronic interaction in free state. So it is almost compulsory, and I assess that it's compulsory, that the interaction between electrons also in the binding state is intermediated by another kind of bosons. So the bosons I call bondon, from bonding. So you can search immediately on web bondonic theory, you will find my papers. And one I quoted also, the original I quoted also in my report, it is from 10 years ago. And according with this, as a particle, it can have an operator, because they are operators of creation and annihilation corresponding to particles. So if you see a complete picture of quantum chemistry in a good tradition of the quantum mechanics and philosophy at the large, wave function of chemical bonds should have also an associate, at least quasi-quantum particle of chemical bond. And for that kind of particle, you can formulate operators. Okay, maybe you disregard this because you were I understand by reading the thesis that you made the computation, were astonished and impressed by so many results, sometimes divergent. Some microphone is somewhere, whatever. You see some microphone open. So you can think for making. Thank you, Radu. You make things to make a further step. If you want to do that, I will do it. So I offer also cooperation via Radu or directly or whatever you want. In this new project of shaping of or characterizing chemical bonds and all interaction, all the dynamics, all everything in terms of completely quantum mechanical approach via quantum particles. A part of this, which I put it, I mean, also in constructive way, because it is stimulating by the philosophical approach and by your conclusion, which now you understand, I understand it is so drastic. And I have an obligation scientifically and morally to make you warning that some theories putting the chemical bond as an observable through the quantum particle, by the way, that's bondons, which I characterize for some paradigmatic chemical bonds, have a specific mass, a specific action radius, specific velocity, and a specific time of life. So in a specific, in appropriate femtosecond spectroscopy, you can even detect such quantum particles of chemical bond. So it should have also some observable character, of course, not at the large time scale, but the specific nanoscale of which they are characterizing. Yeah. So a part of this, the thesis is very comprehensive. I like it very much. I like it. I like the. I understand the spirit of it. So characterizing the metalloboron, then putting at work in a receptor situs, making out of the conclusion of Cuban influence and role and so on. So I appreciate very much. The papers are also impressive, are reflecting the high society you were involved. So only as a question will be, for instance, for the sake of scientific discussion, will be if you would try to introduce the temporal analysis in some parts of your intermediates, or either in optimization, either in intermediate transition state computation. With which quantum chemical tool you will associate, and in which phase you feel that temporal addition dynamics would make a difference or will enrich your data or perhaps conclusion, whatever.
Yes, well, you would have to do TD-DFT for the first, and in which case it would make sense. Now, yes, when you have the electron additions and the proton additions, maybe there you might actually look at something like that.
Yes, I correlate also with the previous discussion, which comes first, electron or proton. Very nice discussion.
Yes.
So maybe the temporal evolutionary or evolutionary operator, whatever, maybe will help also in clarifying this mechanistically, because I saw you pointed at the mechanistical part at the end, which is very important. So maybe you can also discern in this mechanism among the electronic transfer, protonic transfer, whatever.
Yes, and I believe that right at the beginning of the project, so this was like 5 years ago, I think we discussed about doing TD-DFT, but I can't really remember now what was the reason, but we didn't find actually, it would not bring enough information, I mean, relevant information. And from my point of view, I wouldn't actually do that now either. What I would actually do is look at the kinetical aspects of that, because now what we've done here is just the thermodynamic aspects of going from one intermediate to the other. So, for instance, from here to here, but we didn't calculate the transition state. So when this hydrogen binds here, if you do that, and that's on a long term, another plan to do. See how this cluster being present there, how does it affect the transition state, and therefore how does it affect the speed with which the reaction would occur from one intermediate to the other. So you see, I would do it not directly, but indirectly via kinetic aspects. At least that's how I would start.
Yes. Well, usually kinetics deals directly with the observable variables, while dynamics goes to the structure. So there, because the time will brings you closer to that kind of operators corresponding to the so-called non-observable entities as time. Yeah, but well, and then. Corroborating with this, your other assertion that chemical bond has no operator, but it can have, as I told you, via creation operators. So you can, an annihilation, because it's an acceptor-donor process, of course. Then maybe via evolution operator and in perturbation approach, you may get out some more sequentially mechanistical view, so to speak. Mm-hmm. So this is my, well, just for being constructive in discussion. So adding time, I think it's a next step. Also because it also it is virtually important also for the biological activity which you seek to evaluate, because it is also not a static value. Yeah? So okay, you can use some kinetics, but if you want to understand the mechanism, you should go to the dynamics. Then it's important to see which comes first, eventually with which leg, with which intermediates, with which apport of electrons, and you may understand eventually you can add with other atoms or other metals to support or to release other electrons in the process, to catalyze them more or less. So you can play with that.
Well, yes, I would add to that actually you could approach, even starting from these kinetical aspects, you could approach those dynamical aspects. So not in the terms that you described, but while still grasping the dynamics in time. If you do those kind of calculations, so you start not only just doing the transition state, there are some other kinetic theories, quantum theories that you can actually more you can use, and then eventually you would arrive at some kind of a framework which is based on Marcus theory. So that's quantum tunneling, so that you do it in time. And yeah, but you see, I went just on the other branch of dealing with time, not in the way you were dealing, but your approach was interesting as well. And yeah, it would be very interesting to actually discuss this face-to-face at one point and see how further it will go.
Yes, the only point is that the kinetic approach deals mainly with the averages. So you average after all, so you cover everything which is inside, all the quantum histories, all everything, in order to get kinetic parameters at their macroscopic level, so to speak. Mm-hmm. So after all, I have to write, I like, and it's my pleasure and honor to write the conclusion that your thesis, it is a great contribution in computational chemistry in general, in Romanian special, and I appreciate very much the hints this thesis brings and the courage, at least affirming that computational chemistry using quantum chemical methods, even at a very advanced level, are not enough for telling the truth, the epistemic level about the chemical bond. So something is still missing, and it's my claim that missing is the quantum particle of the chemical bond. So, but for all this, your findings and courage of assessing and affirming the missing things, maybe not explicitly with this particle, but in general, that something is still missing for the Socratian conclusion at the end, you fully deserve Ph.D. in chemistry. So please don't stop it and continue.
Thank you.
Thank you very much for your evaluation. And now I will invite Professor Vasile Kish from Babeș-Bolyai University. It's your turn now, please.
Yeah, okay, I hope you can hear me, yeah? Everything's okay?
Yeah, it's okay.
Good. Of course, being the last referee, there is not much left to be said after the PhD supervisor and the other two referees. And I have to say from the beginning that I'm honored to be a member of this jury, and thank you, Radu, for the invitation. Well, my report is about 3 pages long, but of course I won't read everything. But let me emphasize something which I like to this thesis. First of all, it was a challenge indeed to read and follow the ideas presented within the thesis. I think Adrian made a nice and inspired mixing of science and philosophy, which made this thesis certainly a non-classical one, but also very pleasant attempt for the readers. As Radu also mentioned, and all the others, the thesis is well equilibrated from the content point of view. The obtained results are new, clearly new and original, and with an important impact in the field. Part of the published papers have been already cited in the scientific literature. And the fact that 9 peer-reviewed publications already emerge from this work, from this thesis, further emphasizes its quality. The core thesis is divided into 2 chapters, well, chapter 3 and 4. I would say that the third chapter of the thesis, even though it seems a little bit, how to say, dry, yeah, I think it's actually, on the other hand, a PhD thesis by itself. There is enough research done and enough results in this chapter to be considered like that. A huge amount of work had been done and is reported here. If I counted correctly, a total of 150 complexes were analyzed from the geometrical structure as well as the skeleton electrons point of view. And it is worth mentioning that some experiments related to the synthesis of hydrogen-rich metalloboranes have been initiated by the results published, obtained in this thesis. The fourth thesis is a little bit, yeah, is more juicy if compared to the third one. It has been analyzed. The work is very nice and with very good and original results. Now let me say which are the most important results, in my opinion, of this thesis. Well, the author succeeded to explain the structures of and potential energy surface for 27 hydrogen-rich metalloboranes complexes with 10 transition metals. He clarified the effect of cyroheme modification within sulfate reductase active site, as well as the effect of cuban and cyroheme system. Established the best computational methodology. Well, that's a benchmark, but such benchmarks are very costly from the computational resources and time point of view. He analyzed the redox potential of cyroheme centers and the interaction between the two cofactors, explained the differences in the electron transmission properties between the cyroheme-cubane and heme-cubane systems, established the mechanism by which SIR reduces sulfide to sulfide, and also explained the role of cuban cofactor, the catalytic cycle of SIR, and the role of the protein environment on the mechanism by which this SIR reduces sulfide to sulfide. Well, finally, it is worth mentioning that Adrian Brânzanic is co-author of already 9 published papers in high quality, very high quality scientific journals with impact factor per author of 9.8 and a total article influence score as high as 6.50. I'm mentioning this value because in physics, for the physics commission of the CNATCU, you need, in order to obtain, without trying to influence the last decision of the jury, in order to get the summa cum laude distinction, you need only 3.5, the value of the article influence score for the published papers. Once again, of course, this reflects the quality of the obtained results and the thesis quality as well. So in conclusion, the magic sentence at the beginning, the contributions made by the candidate provide more than sufficient evidences that Mr. Adrian Brânzanic demonstrated creative abilities and very strong skills in the field of computational chemistry and molecular modeling of biomolecules, and that the thesis is clearly at the standard expected for a PhD degree. The scientific content of the thesis, the novelty and originality of the results entitle me to propose the award of the title of Doctor in Chemistry for Adrian Brânzanic. Well, this was the report, and I have a few questions. First, I will start with the title of the thesis. And in the title, I've seen pH. I suppose it comes from the power of hydrogen, isn't it? What's the meaning of the pH in the thesis title? A pH adjustment, you said.
Well, yeah. Well, it's a metaphor in which you use the pH as pH of a solution. So you adjust. Yeah. I mean, originally PhD comes from a doctor in philosophy, but
yeah, I know, but that pH, only the pH without D, I'm interested in.
Yes, that's the philosophical part, and it's a joke that it's like the acidity of pH. So you use philosophy somewhere where some other people might see this problem more acid. So we adjust, like usually you do in chemistry, you adjust the pH environment of something so you can have that reaction.
Yeah.
So
yeah.
it was a pH adjustment. That was the.
I was thinking that the pH referred to the power of hydrogen, yeah, and I was wondering what would you consider as being the acidity and basicity of a Ph.D.
Yes.
Okay.
Well, you can play around with the thought. I mean, you've read the thesis, and I won't go further into those aspects. But if you just look at it, I don't know, from the Apollonic approach and Dionysiac approach, you can play with it and say one of them is acidic and one is basic. Well, you could go with the Dionysic one to be the acidic one because it's wine and usually it's more acidic. And if you just toys like that. Okay, good. Well, in many cases, I've seen the relative energy window is different for different complexes which are analyzed in this study. Why is this? You choose a given number of complexes or why this window of the relative energy is different for different complexes? And you mean metalloboranes? Yeah. Yeah. So in metalloboranes, you mean? Yeah. Okay, so usually when you do this kind of calculations, well, you have an isomer, which is this is the most stable, and then everything else you compare it to it and see at how many kilocalories per mole above it this isomer lies. So that's like a rule of thumb. If it's roughly about 20 kilocalories, 25 kilocalories per mole, it's probable that you will find it in experiment as well, because at the given conditions, normal conditions in 20 degrees Celsius and 1 atmosphere, you may actually have enough energy in that system so that you can actually do those higher isomers. So there are cases, for instance, in this presentation where when we had the tantalum and it was only one structure, that was because where is the next lying isomer was something like 25 or 30 kilocalories per mole. So it wasn't worth bothering with it and describing it because, well, unless you really want to synthesize that isomer, I think it would be rather low chance to see it experimentally. So, and in some cases, like they're different. Like here, it's we have in that window. So usually we try to make it in 20 kilocalories per mole. But in this here, I just showed the ones in the first 10 kilocalories per mole. But in the articles, usually they go all the way to the 20. But usually when you get to higher vertices, families, things get more complicated. And we already worked on the 10 vertices system, and then you have in the 20 kilocalories per mole interval, you can have even 70 isomers. So then we have to change all this because it's kind of too much. But that's the rationale behind it. That's why we used, usually we guided by the 20 kilocalories per mole window and see how many, and we describe the isomers that were found in that energetic interval. Okay. And what is the energy? That energy is the SCF energy, or it is corrected 0-point Babeșian energy? Or yes, in the case of metalloboranes, they are all corrected with 0-point energies. Yeah. Well, maybe using the Gibbs free energy would be an option also, because yes, the thermal effects and so on. Well, actually, yeah. Basically, yeah, again, the information is there because once you do, so this were done actually in Gaussian, so all of them. The metalloborane project was done in Gaussian and the sulfate reductase was done in Turbomol in Lund, in Sweden. So when we used, even in Gaussian, you have at the end of your outputs, if you do the frequency calculations as well, they give you the free energy and also just the enthalpy and the 0-point energy as well. Mm. Okay, on page 181, you are comparing the triple zeta and double zeta basis set, and you say the triple zeta basis set fails in describing correctly the spin state of the ground state for some density functionals in case of model A. Do you have any explanation? Because, well, normally we expect that increasing the basis set flexibility
we expect more accurate results, of course.
I don't have an explanation, but I have a hint. So it's like, it's this kind of effects when you put actually too much in the basis set. And I mean, you put too many basis functions in the basis set, and therefore sometimes you might actually have this kind of errors. Like, well, I can't remember now how that's called. It's regarding with the spin when you have basis set superposition error. When you have this kind of things, just because the basis set is too big, and then, well, you add too much amplitude on that atom that probably it wouldn't be there naturally. So, but in your mathematical framework, you add there because you want, yes, to have more flexibility. But in doing so, perhaps you are just overshooting this over flexibility. And yes, it was a surprise that actually it was the same and sometimes even better with the double zeta, and basically that was the reason behind when we dealt with the substrates in the sulfate reductase project, we just decided to keep it at the double zeta level of theory because the calculations on the triple zeta level of theory, even albeit just single points, took very much. I mean, in terms of days. And the one with double zeta were going just, on the order of 1 day.
Okay. And the last question is related to the redox potentials for him and Saruhi models. Something seems to be wrong here because actually you emphasize that a systematic error in the calculation most likely arising from the charge and polarization of the models. What about the methodology? Did you use the Born-Haber cycle to calculate the redox potential, or?
No. This is simple. I mean, this we followed. So Nudelman is the person who worked, I think, from the beginning of the 70s on iron sulfur cluster, and actually he developed the broken symmetry methodology as well. And we just used the way to calculate redox potentials as emphasized by him in this paper. So basically, you're just translating, the ionization potential, but you do it in vacuum, and then you correct it via the ones that in the solvent continuum. So no, it wasn't any cycles like that.
I see. Yeah. Okay, it is clear because, well, in that Born-Haber cycle, you need to calculate also the solvation free energies for the system, and probably because the error is it's high. Yeah.
Yes.
But when compared to calculated values with the experimental part.
Yes, but we weren't aiming to find the precise or close to the experimental part. We didn't care, but we just wanted to. That was the advantage of all this project. We were always comparing him with Saruhi. So any type of error that you included in one part, you included in the other one. So then you have cancellation of errors. So that's why I didn't even emphasize that. I think experimentally so this would be like 1,100 millivolts redox potential, and experimental I think it's like 390, somewhere around there. So it's like almost 4 times bigger. But we didn't care about that. We compare just how him and Saruhi go, and that's the reason why I didn't even bother going further and having a precise value.
Okay, I understand. Okay, and thank you and congratulations, Adrian.
Okay, thank you.
Thank you very much for your appreciation and for your questions. I also saw that we have a large audience on the net, but we also have some colleagues here in the lecture hall. So I have to ask if there are any other questions. If yes, please address them. Dacă nu vreau să mă... There are no So, no one raised his hands, so there are no any other further questions. From here.
No, we have one from the.
Yeah, sorry. Mate, please. But I will invite you to come here, please.
Okay. First of all, I want to congratulate Adrian for his work and presentation. You did a very nice job, and regardless of the philosophical adjustment of PH in your title, you have also provided insight in things that we are interested in. I've been impressed by the fact that you tried to explain what happened with this difference between heme and cyroheme in this enzyme. Even if they look similar, they don't behave quite the same. And this is our job as scientists, to try to come up with these answers. At first we study things, then we come up with rules, then we try to extend the rules, and then we find out they don't work on other systems, and now we have to find answers. Eventually we come up with a different set of rules, and so on and so forth. My question was related to the studies you did on clusters, on the metalloborines. Because you have presented thoroughly this part on the hemes, but you sort of went faster on that part. And at the beginning, you told us about the three standard types of geometry, closo, nido, and arachno. And that would be, let's say, the basic rule. We have the Waite-Mingus rules that tell us, based on number of skeletal electrons, which geometry we're supposed to get. But we don't always get that.
Yes,
the Waite-Mingus rules work pretty well for the boranes, but your systems were metalloboranes. You had the substituents there, you had metal atoms capable of multiple bonding and so on. So since you only briefly discussed these clusters and even skipped some of them, I noticed you did a lot of calculations, and my question is regarding these systems. How often did you bump into a situation where Waite-Mingus rules were not respected, and how far did you try to analyze them to find an answer why this didn't happen?
Yeah, okay, so thank you for the question. Well, it was, well, first of all, I presented, that was one of the reasons why I presented the 5 vertices, because that was the place where actually the Waite-Mingus rules worked. So they worked for all of them. So that was easier for the presentation to just show where it works. But yes, in the higher families, not all the time, they're not working. But the way I see them is that, well, they are not laws, they are rules. So they are destined to break at one point. And all the time, usually they break when, this is like in paradoxes, when you have a certain framework of thinking and you apply it in a different framework and you see that it's not working. So it's kind of the same here as well, because I will just go to show you. There are cases where actually, well, there's, yeah, so for instance here, in the first window, Waite-Mingus rules were referred to closo, nido, and arachno, and you could have argued that, well, the isocloso was something which violated these rules, because you would have for instance, in this case, so 7-vertex system that did not obey the Waite-Mingus rules, because it has 7 vertices and it has a 2n electron rule. So this is when you apply a framework of thinking, of counting it like that. So that's, well, it's not working. But if you actually look closer to the system, you realize that, well, this is not really it's not actually working like a vertex, like in a normal sense of the most spherical deltahedron vertices, but it looks more like a fragment that binds to to the face of the polyhedron, so it caps it. So when you think about that, so that's a BH here. So let's say that a BH fragment that donates 2 electrons, but that it donates it here. So that's why you would have. So if you don't have this vertex, you have 2n plus 2. But now you have it here, but you have the electrons, but you don't count this as a vertex. So then you would again come to the 2n plus 2 if you think about it like that.
Yes.
So this is how I see the Wade-Mingles rules, that they work in some framework, but yes, they will not. I mean, it's not the end of the world if they're not working. It's just meaning that something more subtle is happening, and you have to take account to those electrons. How do they end up there? How do you count them there? Because at the end of the day, what basically it's very deep inside, and which is common in all of these metalloborane structures. So if you, like I would say in the thesis, this, the suprasensible reality inside of these metal boranes is actually the internal structure, their electronic internal structure. Because basically, whenever you're doing a closal, like either you put it here or here, basically, and even when you are doing a nido, you're just taking one vertex, but you're keeping the electrons. So you just keep the molecular orbitals or the cluster orbital that is here functioning. So that's actually the core truth inside of this system. So this is how I see them. So when you do Wade-Mingles rules, you're at a higher level, and now you're looking at them as counting the vertices. So yes, not all, in most of cases, and in the borane case it works, but in others it doesn't. Simply because the problem is a little different. It's wider.
Okay, thank you very much.
Thank you.
Thank you very much. If there are further questions. There are no further questions. So normally I should address your question, but I would like to say something instead of a question. You told us that your title, that PH in PhD, it was a joke. I suppose it was a very serious joke, isn't it? It's okay. It was a metaphor.
Yes.
Because you know, the human existence had all that for thousands of years had 3 dimensions. You know, science, art, and spirituality, and all 3 dimensions were formed an indestructible unit. I don't know what happens, but maybe 400 or 500 years, 400 years ago, the spirituality was evacuated from this unit. And after that, also science was divided from art. And I think so that science, without the other 2 dimensions, it's not a comfortable place, you know. So also the philosophy started to disappear from science. You probably know that Newton had no mechanics studies. He wrote philosophy books. Dalton's book, it's not a general chemistry or inorganic chemistry book, if you want. It was a philosophy book. Yeah. And what you wrote in the introduction, it was a very good, I appreciate very much this idea. Of course, it was your group idea, I suppose. Yeah, and I'm glad to see that Professor Silaghi tried to bring back this science under the roof of a real science philosophy. You know, not that false philosophy which is occurred mostly in the 20th century. So there are just a few scientists who are also philosophers nowadays. And it's not good, in my opinion, because the real ideas cannot be, they have no possibility to occur real, valuable ideas, you know, if these three dimensions are not in the same place here. So thank you very much. And now the committee should be drawn to deliberate, but for this reason, I think that we will start with another channel. I don't understand exactly.
Yes, so what we can do, I'm asking the members of the committee to log into the other channel. There is a private channel in this Teams group. I'm hoping you can see it, and we should log into that to discuss our verdict, and then we'll come back to this meeting to announce publicly the result after we've decided. So for everybody else, this meeting will remain active until we return, and we'll now move on to the other one, the private meeting of the committee.
How do we log into that one?
Yes.
Have you sent a link, or what should I do?
Can you resend or?
Okay, I'll let me check that real quick. Da.
Nici tu nu știi link-ul, am înțeles.
Ca să deschid alt canal, dar a fost același. Servus, Vasile.
Salut!
Te văd, ai colecția în spate de literatură.
Ce mai faci?
Ce să fac? Uite, cu fetele mică, adică a mare, a mea, clasa 6, aici altă cameră online, îți dai seama. Suntem în bibliotecă de conferințe aici.
Aveți destulă bandă pentru internet acolo.
Da, destul de bine.
Nu destul de probleme.
Pe Telecom sunt, da, pe Telecom sunt. Voi?
Noi, Andrei, încă e în vacanță, da, abia la 1 octombrie va începe masterul. Dora la muncă, eu
Dora tot acolo?
tot acolo.
De-aia trebuie să meargă fizic.
Nu e obligatoriu, dacă am avut admiterea la doctorat și trebuie să termine tot felul de dosare și fizic. Știi?
Da.
Și apoi ăsta e motivul pentru care se și duce. Orarul, mai vin colegii la orar, știi, să-și ceară...
În vara asta ați fost pe undeva?
Nu, doar acasă.
Și noi. Trebuie să-ți termini poze de la Giroc. Am gătat, cum se zice, dar nu ne-am mutat încă definitiv, că mai am un pic cu dușurile, cu alea, dar...
Și când vă mutați? Când?
Păi, acum un pic de dificultăți mai avem și cu dusul la școală și cu adusul. Așa cam peste un an, probabil, până fetele se obișnuiesc că este autobuz Giroceana, se cheamă Timișoara Giroc. No, să vedem cum o fi acum cu pandemia asta, în niciun caz nu plecăm de dimineață. E foarte aproape de Timișoara, cum e Floreștiul la voi, știi?
Da.
De fapt, Girocul și Floreștiul și încă câteva comune în România sunt în topul ăla select de cele mai dinamice localități în România. Și acum a luat-o pe arătură, în sensul în care la intrarea în Timișoara au început să facă blocuri, îți dai seama. Deci,
evident.
Pe urmele Florești.
Au și dezavantaje, știi, traficul în particular.
Avem 4 benzi la Giroc.
Atunci e bine.
Da. Nu e așa. E în sud, în zona ardențială, se termină cu Timișul. Nordul, care e cu aeroportul și spre Arad, acolo e Dumbrăvița, și are și Continentalul aproape, acolo e mai poluat, acolo e chiar o nebunie dimineața, câte o mașină pe sens, deci ceva incredibil. Dar la Giroc e ok, nu. Încă se zice că e dormitorul Timișoarei, știi, că
exact.
Nu mai nimic după. Deci Giroc, ca în ultima cameră, cum s-ar zice.
Da. Păi așa e și Floreștiul considerat, într-adevăr. Tot 4 benzi și la noi, dar degeaba, când e aglomerație. Acum că se duc elevii la unii, la ore diferite, stau puțin sector, nu e chiar așa rău.
Da.
Dar era critic. Deci dacă nu porneai înainte de 7, era greu să ajungi pe 8. Da? Dacă pornești înainte de 7, ajungi pe 7:30 în oraș oriunde. Da. Dacă pornești după 7, nu mai ajungi pe 8. Asta era ideea.
Dar cumva, știți, la Florești problema e, nu, că știu că am făcut drumul doar, parcă se îngustează la intrarea în Cluj.
Nu, că se intră pe 4 benzi. Pe calea Florești sunt 4 benzi până...
Intrarea în Cluj e mai strâmb decât... Da.
Nu, e până la USAMV, până dincolo de USAMV, aceleași 4 benzi merg. Da? Până la intersecția cu moților și despărțirea pe clinicilor și pe moții.
Da. Asta e.
Da. Acum, eu am scăpat pe de altă parte, nu mai am probleme. Nu sunt legat de o ora 8 la care să plec sau chestii de astea.
Da, mi-ai zis că ți-ai schimbat modul de viață. Da, eu încă, sunt director de școală doctorală, aștept să-mi vină rândul, cum se zice așa, la o funcție de management mai importantă. Că așa merg lucrurile, știi și tu. Dar, da.
Știu, ai grijă ce-ți dorești, că s-ar putea să îndeplinească, da?
Aia zic, deci un mandat aș dori să, nu de altă, dar poți să mai pui din spiritul tău pe acolo, știi, să mai faci câte un bine, mai corectezi câte un lucru. Aproape că suntem datori, măcar noi ăștia, zic, mai înalți academici, știi, să dorim să ne și implicăm, pentru că, uite, la noi la facultate avem prodecan, lectori, nu că ar fi o problemă asta, dar nu putem să lăsăm numai lectorii și ăsta să conducă, știi, deci, da, în fine. Adică nu că n-ar putea ei, dar sunt niște lucruri, de exemplu, cu promovările, cu, știi, cu posturile, cu astea, trebuie să ai o perspectivă puțin mai largă. Stai că mă sună Radu. Da, Radu, cum e? Dar eu sunt cu Vasile în conversație, deci putem vorbi, eu n-am nimic de ascuns. Eu cu Vasile Chișchi, suntem în direct, cum se zice, unul cu altul. Nu, unul cu altul, dar înseamnă că și l-a rămas tot cu mine. Unul cu altul. Da, pe Teams. Teams.com pre-join call, nu știu ce vrei, ăla se termină cu TAC V2. 19 Cred că da. Toți învățăm, îți dai seama, mai nebunia cu online-ul. Băi, fără discuție, uite, stai că te pun și pe speaker. Deci, fără discuție, excelent.
Mihai și Vasile, noi ne auzim către toată sala, către ceilalți participanți.
Da.
Vă opriți un pic microfonul de la Teams.
Okay, so I'm sorry to interrupt. I'm just calling Wolf, Professor Ryde. I wasn't able to get you on the private channel, and I also tried to call you on the phone, but you're not answering. We need to confer somehow.
Okay. Can you not just start a new Teams, which I can do?
Now I don't hear you, maybe.
You don't hear me? Do you hear me now?
Professor, I hear very well, Professor. He's on the team.
So I hear you.
Okay, so can we please have a brief private talk somewhere else? I don't know, on Skype or somehow.
Yes. I can open my Skype now.
And then, of course, stop your microphone here, because that was the point. Skype. Skype, yeah.
Okay. Okay, so we are back. All the guests are here. I suppose. Okay, fair enough. So, the committee unanimously decided that PhD student Adrian Mihai Vasile Brânzanic can be awarded with the title of Doctor in Philosophy, Chemical Specialization, with the qualification Excellent. Before congratulations, we are passing the word to
Okay, so thank you very much. I'd like to thank all of you who were in all this process near to me and helped me evolve in terms of personal development with regards to, and yes, we did indeed, with regards to this path, the PhD thesis. So I'd like to thank you all, and further thank you will come in the next days in personal matters for each one of you. Thank you very much.
Okay, so congratulations. So with that, I think.
So our meeting is stopped here. Thank you very much for all of you. Thank you very much. Special thanks for the reviewers, and thanks a lot also for the guests. So bye-bye and see you next time. Bye.
See you on the next time. All the best.
Okay. Deci nu vreau să felicitări că
Felicitări conducătorului și doctorului, noului doctor în chimie. Felicitări!
Mulțumim!
Felicitări, domnul Brânzanic.
Stop recording.